Okay, this is the problem from chapter 4 that I'm going to be doing. It's a rotating disk. Okay, so let me scroll down here. So the problem that we've got is a disk, let's say made out of steel like that, and it's got a hole in the middle, and this is spinning in the space. Think about it as being a UFO spinning in space, and uh, obviously stresses are going to develop in it. Now, a couple of comments. First of all, uh, it is impossible to have it. It's impossible to have a disk like that spin in space physically, unless you think about it as being, let's say, a flywheel, or let's say a gear that's attached to a shaft, and the shaft is spinning and takes this thing with it. But we assume that those complications are not present, and somehow this spins in the space. A couple of other comments, and that is, notice that for obvious reason, if you look at all the points which are the same distance from the center of this disk, they all experience the same deformation, the same stress, etc. This being the case, it means that if you take a sector of this disk, irrespective of what that sector size is, 30 degrees, 40 degrees, etc., uh, uh, the story about that sector will enable you to say exactly what the other sectors look like. They look exactly the same as far as the distribution of the displacement, stresses, and things of that nature. Okay? Therefore, in this problem, in principle, you can take any two planes, radial planes like that, and these are planes of symmetry. And incidentally, if you take a cut through this, disk, basically think about it as being I don't know, a slice of cheese or salami, and you cut it in the middle so that you split it into two salamis, two circular salamis, then the two pieces are identical. Okay, so in this problem, as done in the book, I'm not taking that mid-plane cut. But remember, on the final exam, you have to take all planes of symmetry, so you have to include that one in it too. Now, what else do I have to tell you here? I think for now this is okay. Let me go ahead and model this thing. In Catia. So there we are. Remember that this is a single part, therefore I don't advise you to start in assembly. Just go ahead and create a part file, file new, and let's make it a part file. Okay, and don't forget, immediately save this, because everything is going to go into your folder on the test day of the final exam. So file, save management, save as, desktop, new folder, and let's call it rotating disk. Rotating disk. Okay, very good. And save. Okay. Oh, one other thing before actually I make this model, I want to go to this graph. This is the kind of problem that we used to do in stress analysis. There are three principal stresses in this problem. There is the radial one, the hoop stress or tangential stress, and there is the axial one. We are assuming that the axial stress is zero, it's almost zero, because notice that there's nothing that confines this part from shrinking in the axial. Axial means the z direction, upward direction. Okay, that being the case, there is very little stress there, so it's fair to assume it's zero. The hoop stress and radial stress, there are analytical expressions which can be found through these formulas. The omega is the constant angular speed, R is the density of the material, steel in this case, and Ri and Ro are the inside and outside radii. And obviously mu is the Poisson ratio. You can see that the biggest stress here's a hoop stress, you can see that, this is the hoop stress right there. The biggest stress is on the inside, and it's a hoop stress. And on the outside of that disk, of course, the hoop stress is present, but it's not zero. However, when you look at the radial stress, on the inside, radial stress is zero, on the outside it's zero, and the maximum radial stress actually occurs sometimes somewhere in the middle of the part, which is very unusual. Okay? All right, so let's go make it. So I'm gonna, on that vertical plane, I will sketch a rectangle like that. And let's give it dimension. The inside radius is 1 inch. Not this. Sorry, delete. Let me delete this dimension. Okay, I want to try to delete. Okay, this dimension I want to delete right now. Oh, how come I cannot delete it here? Let's see. Delete. Okay, good. So dimension between this line and this axis, this is 1 inch inside radius. Okay, and the outside radius is going to be 6 inches. So why don't I make this thing 5 inches instead? I'll do the same thing, 5. Now, as I pointed out in this problem, I'm not going to, this height, by the way, this height, the height of the disk, we're assuming it's 1. And I told you that in this problem, in this analysis, I'm not going to use half of that because there is a plane of symmetry right in the middle, right in the horizontal direction. There's a plane of symmetry, half inch up, half inch down, but I'm not going to do it. Okay, I'm gonna, as it's done in the book, I keep it like that. On the exam, make sure that you use all planes of symmetry that are applicable. Exit, and then we're going to shaft this. We shaft it about the z-axis. Put the cursor there about the z-axis. And we don't want to go 360 degrees, we want to go 30 degrees. That angle is completely arbitrary. I'm choosing thing 1. Okay, let's apply properties of material to it, of steel to it. So where is the apply material here? Oh, okay. Now, I don't see my apply material in my toolbar here. Maybe I accidentally deleted it. You can always reset your toolbars, or you say view, toolbars, apply material. Let's find out where it is. Apply material, right there. It was close. And let's make this thing out of steel. So metal, and scroll down, and steel, and on that. Okay. Now, I'll keep these default properties. I will not change it to whatever it says in the book. So I'm going to save this thing and then go to the generative structure analysis. Analysis and simulation, generative structure analysis. Catia immediately measures this with the size of element that you see there. There we are, and let me change the rendering here so that you can see the edges right there. Now, this is a terrible mesh because we know that there is going to be a gigantic stress distribution, or let me put it, a severe stress distribution at the inside of the hole, Okay, so we need a fine mesh in this area. I still have not told you how to do fine mesh in a particular area. The trick we're using, we make everything small, which is not a good strategy. But let me try it. Let me go here. Double click on that. First of all, use linear element, which is not as good as parabolic. Maybe I should go to parabolic. And then I use a smaller size element, so I make it 0.1. Here, maybe 0.2. Okay. And now let's look at our mesh. It's a bit more unnecessary because there's no reason to have small stresses, elements in this area. We need to have small elements around in the critical area, which happens to be right around the hole. But leave it the way it is. I'll have another video segment for local mesh refinement later on. Okay, so this is all done. As long as this is in front of you, there's nothing you can do. So I'm going to hide this. Or deactivate it. Okay. Now, that's a plane of symmetry. Okay, this is a plane of symmetry. Notice that this guy is in the YZ plane, and it's a plane of symmetry. So I'm going to use surface slider over here on that face. Now, I can do exactly the same thing on this, and in fact, it's a lot easier if I do it like that. But I want to make it more complicated for you because there's a few new things that you're going to learn as done in the book. So I'm going to cancel that. I'm not going to use surface slider here. You should have. If you're using a cut in the middle to take that mid-plane symmetry, you also have to put surface slider there. But I want to show you some new tricks. Okay. First of all that surface slider means is that there is no displacement perpendicular to this plane. However, the problem is that this plane that you see here is at 30-degree angle. So being 30-degree angle, it's neither aligned with X, nor Y, nor Z planes. So what we're going to do, we're going to create a local coordinate system. So how do we do that? We have to go back to the part. There we are. This is the part. And here is a coordinate system. See that? It says axis system. Click on it. It says, where do you want the origin to be? I want the origin not to be at the default, which is over there, but at one of these corner points. Now, this corner point is on a plane that is at 30 degrees. Now, the XYZ is still aligned with the XYZ global, which is not what I want because that's the only reason I'm using local coordinate system. So I can choose the X, any of these edges to align X on it, to put X on it, or Y on it, or Z. So let me try, for example, let me try to say that I want my Y axis to be this line. You see that? Y is along this, and X is perpendicular to it, and Z is up. So if I want to say nothing moves perpendicular to plane, I can select this coordinate system later on, and I say, hey, nothing moves in the X direction. Just be aware of the fact that the way things, this coordinate system is done in the book, it could be that I put X on that edge or Z on that edge. I don't remember, so I'm not going to try even to duplicate that. By watching this video, you know what's going on in the book. So don't try to just copy everything that's in the book without knowing what's going on. That's not going to help. There we are. We go back to analysis. Notice that we now have a coordinate system in the direction X is perpendicular to that plane. Now, let me remind you that we have to save this thing. Save management, the analysis, we're going to save as in that same folder, rotating this. I'm going to keep everything there so that if I ever have to get out of Catia, I don't lose this stuff. Okay, now, instead of putting surface slider here, we use this coordinate system, made it life more complicated because we want to use it. So now you go and select the, see that right there? Not the surface slider, but user-defined restraint. User-defined. You click on it, and notice that the coordinate system that we want to choose is not global anymore. Global was no good. Global is over here. We rotated this so that Y lies on that edge. So you're going to select this thing to user because we defined one, and then it says select it. There it is. We selected it. Now in that user coordinate system or axis system 1, we want to say there is no displacement in direction X right there. See that? X. So no coordinate system in direction 1, which is X, Y, and Z. What I mean is that X, Y, Z of this coordinate system is 1, 2, 3. These rotations have no bearing on the problem because we're using solid elements. We have discussed that numerous times in the class. Now for support, this is the support. Notice that it says that nothing moves perpendicular to it. Excellent. Kill it. All right, save everything. Now we want to say that this guy rotates about the center of this hole that we have in the middle. Okay, so let's look at our loads. Where are our loads? These are loads. We know how to do pressure. This is not a pressure problem. We know how to do force. This is not a force problem. This is linear acceleration. For example, accelerating in a certain direction or gravity. Now, if you go there, there's also something called rotation force, because what is happening in this disk is the centrifugal force or rotational acceleration. Rotational acceleration. You click on it, and it's very simple. It says support. This is a body force, so it doesn't matter what you pick. It always picks the entire body. No problem. Rotation axis. Well, rotation axis is right here at the center of this hole, but unfortunately, I don't have anything to pick at the center of this. If I had drawn a line here, I would have been able to pick it. See that? And if you right click, it won't let you do that. So I'm going to use a trick. The trick that we have alluded to before is you go and create a local coordinate system here and use its z-axis for that purpose. So back to part, because local coordinate system or axis system can only be done in parts and assemblies. So you click on this, and the origin is what is this? Let me cancel that. Okay. So it's going to create a coordinate system here, at least it should, at 0, 0, 0. So let me see if it does. Why is it not doing it? Hang in there. Okay, this is not what I want, so I'm going to delete this. The first one is that we wanted. Fine. Okay, so let's go to the part. There. Okay. So I don't know, for some reason it didn't do it the first time, and it put one on top of that, or I want it, and I want the origin to be exactly where it is, in other words 0, 0, 0 global. The only thing that I need here is that z-axis, that's all. So back to, maybe you should save this, back there to analysis. You can see that it's sitting here. Again, rotational force. The support is the body. Doesn't matter what I pick. Rotation axis is that z-axis, or any line that you add here. In fact, if you zoom in, you see what you got here. It's kind of rotational axis symbol. Now, right now the speed is given in RPM. The problem that I have there in the book, I'm saying 113 radians per second. Now you can write it in radians per second, but I don't know what. Let me use 60 RPM. 600 RPM, okay? Now, I don't know, 600 RPM may not actually turn into that 113 radians per second, but I don't want you to memorize these things, so you put the right speed here, whatever it happens to be. Okay, in the book it says 113 radians per second. You can convert it and find out what it is, and there's no angular acceleration here because this is going at a constant speed. However, if this was a disk that was starting up, speeding, or slowing down, then you have to put the corresponding angular acceleration here. But for the present problem, this is constant speed. So we say okay. Now we're almost done, and let me run it and show you that it will not work. There is something that we have forgotten. So let's see now. Where is the? I always suggest that you save before you run. Okay, now run it. I think my computer went into coma. It'll come back, but if for some reason I had to kill this job, Control-Alt-Delete, kill Catia, if I had not saved this thing, everything would have been lost. All right, it did come back. Don't worry about the warning message. You always get that. Most of it get that. Okay, you can see it didn't run. And do we know why it didn't run? Let me try to animate the motion. Although it didn't finish, but at least I can have an idea of what the problem is. The problem is that this thing can move as a rigid body entirely in the vertical direction. If I had used the middle plane of symmetry and put surface slider, this would not happen. But that's okay. Well, I didn't do it. So let me stop this thing, deactivate this plot, deactivate this, and now prevent motion in the vertical direction of a single point. That basically pins it down. So you say, where is that? User defined, there, user defined. Now you can use the global direction or the user direction because the z-axis is exactly the same. It really doesn't matter, but pay attention to your own problem, what you're doing. So for example, here I'm going to say that one point does not move in the direction 3 of the user system, which is that direction. Okay, I could have used global, the same thing would have happened. So what is that? Right, it says user, and obviously I have to select this, or as a matter of fact, or that doesn't really matter because they're two user systems. That's okay. This one here, look, cannot move in the upward direction. Here it was waiting for me to say, okay, you are saying user, so which one is it? There's two of them. There's the first one and there's the second one, and it really doesn't matter. Both of them Z is up. So now when I run this thing, it will work. And it's done. So you can look at the, first of all, the deflection, average ISO, change this thing to material shading. What is this? What did I plot? Translation of displacement magnitude. Let me get rid of this. Let me go there, see what I did. Average ISO. Oh, you know what? I'm really sorry. My computer, this computer, does not give you the correct. It's my graphical problem with this computer. It does not give you the correct. You know, contour plot. It is correct, but because of the graphics on this lousy computer, it doesn't work. Let me try to do it a different way. So I think, I'm not sure, but I think when it's linear, it may be giving it to me. I'm not 100% sure. Let me see. Let me run it with linear. This will not happen to you on the in the lab or on your computer. It's just this particular computer, which is quite old and got a bad graphics card that's not working. Let me try. Let me try see if the linear one actually gives it to you. So translation, yeah, you see that? Quadratic does not work on my computer. Terrible. Okay, now this is obviously the biggest displacement is at the outside. The smallest one is on the inside. And let's see now, the 1 meso stress, there is. The biggest stress is right at the inside is the 1 meso stress, and very little, well, compared to this, very little on the outside. These numbers are very small because if you think about it, it's a 1-inch thick piece of steel which is rotating at 600 RPM, which is really not a big deal. Okay. Now, by the way, if you, yeah, so let me just have an idea of 600 or, well, yeah, I'll just leave it the way it is. Okay, folks, there's also, you can also plot the, what is it called, the principal stresses, and it looks like that. If you zoom in, you see that at every point, you have, at every node, you have 3 principal directions: radial, hoop, and axial, and the numbers are little knowledge. So this must be the, this must be the radial stress. This is the hoop stress, which is bigger, and the axial one is very small. It's something 10 to the minus 6. Yes, well, I mean, you can assume it's 0. It's 10 to the minus 6 compared to these things. All right, I'm going to stop here, and the hope that you can use this thing while I'm gone.